Hello there, welcome to chapter 8. Okay, so for today we will look into example 8.1. Okay, you have a double slit pattern, okay, view on a screen, okay, which is 1 meter from the slit. Okay, so this will be the distance, okay, from the slit to the screen lah. Okay, if a third order minimum, okay, are observed 25 meter apart. Okay, so this one they have mentioned 25 meter apart. That means the distance between two third order minimum. Okay, so they wanted to calculate the ratio of the wavelength and separation between the slit. Okay, and then B, distance between first order minimum and fourth order maximum on the screen. Okay, so now the information given, okay, distance from the slit to the screen, okay, and then the separation distance, and then the order lah. Okay, so you have a third order. Okay, alright, so for better understanding, what we do is that we sketch it. Okay, so over here we have the maximum order, okay, which will be the zero order. Okay, so now the distance separation is between from the third order, from the top portion over there to the third order to the down portion over here lah. Okay, so slit separation, and then from the slit to the screen. Okay, so from the figure we can determine the separation for one order lah. Okay, so basically for calculation we will either calculate on top side or bottom side only. Okay, so by dividing 2 we will obtain this value. Okay, separation for third order from the zero order. Okay, okay, now by applying the equation for the dark fringes. Okay, so dark fringes you will end up with order plus half lambda d over d. Okay, replacing the value. Okay, now we want to determine the ratio. Okay, so ratio of lambda over d. Okay, so just solve it lah. Okay, so you'll end up with ratio which doesn't have a unit lah. Okay, lambda over d, unit will cancel off. Okay, and then to find the separation between the central max and first order minimum, okay, we can apply back the ratio over here. Okay, so which will end up with one equation. Okay, and then for the fourth order, redo again. Okay, so to find the separation distance, just minus lah. Okay, minus with the fourth order with the first order. Okay, so we already have all the value. So either what you do, you replace in the value first. Okay, end up with the value, just minus the difference, or you can do it like this. Okay, in the end we find the separation lah. Okay, so which will end up with 8.93. Okay, example 8.2, they wanted to explain. Okay, they wanted to explain how would you expect the interference pattern of a double slit experiment to change if white light is used instead of monochromatic light. Okay, now what is the meaning of monochromatic? Okay, so mono, that means you use a light with only one wavelength only. Okay, and then B, describe the changes that will be observed in a double slit interference pattern if the experiment was submerged in water. Okay, so you conduct the experiment in water. Alright, so for solution A, so the location of the bright and dark fringes depends on the wavelength. Okay, it depends on the lambda lah. Okay, therefore if you use a white light, okay, through a double slit experiment, okay, bright fringe will show some separation into colors, giving a rainbow effect. So basically white light consists of all the spectrum lah. Okay, a lot of wavelength, so you will have separation of wavelength, so that means you will observe a rainbow effect lah. Okay, B submerging into water. Okay, so basically what will happen is that the wavelength will reduce lah. Okay, from lambda to lambda over n. Okay, so n over here is 1.33. Okay, so therefore the bright or dark fringe separation will be reduced lah. Okay, so the separation will reduce and the fringes will get closer to each other. Okay, because over here lambda will reduce. Okay, so when the lambda reduces, okay, lambda reduce, so when the lambda reduces, okay, lambda decrease, okay, delta y also will decrease lah. Okay, so for example 8.3, so in a young double slit experiment, okay, we have a monochromatic light. Okay, so wavelength given as 600 nanometer. Okay, shines on a double slit. The fringe separation of the interference pattern is produced 7 mm. Okay, and then when another monochromatic light source is used, the fringe separation is observed to be 5 mm. Okay, they wanted to calculate the wavelength of the second light. So the assumption over here is that we are doing the experiment, for example. Okay, so we use two different light source. Okay, assuming all the other variables are constant lah. Okay, so only information that we have is that this one, okay, wavelength, the separation, okay, for the first one, and then separation for the second one lah. Okay, so what we can do is that just simply draw for the first case. Okay, so for the separation, either one lah. Okay, either it can be separation between two bright fringes or two dark fringes lah. Okay, which will end up with the same value. So assume over here your D, okay, separation of the slit, and then the distance from the slit to screen is constant lah. Okay, so just form an equation, okay, based on the given information for the first situation. Okay, and then form another equation, okay, for the second situation. Okay, so which will end up with two equation. Okay, so therefore we can solve the problem by using simultaneous lah. Okay, so over here they use second equation divide with first equation. Okay, from there you will end up with lambda equivalent to 4 to 9. Okay, times 10 to the power of negative 9 meter lah. Okay, or 4 to 9 nanometer. Okay, for the last example for double slit, okay, example 8.4. So this one you have two coherent source S1 and S2, light in phase. Okay, and then the separation of S1 and S2 is given. Okay, separation of the source. Okay, and then the screen is 2.5 meter from the source. Okay, separation of the screen. You already have it in the diagram over here. Okay, 1.2 and 2.5. And then over here the frequency is given. Okay, they wanted to calculate the wavelength of the light used. And then number 2, separation between two consecutive bright fringes. Okay, if the experiment carried out in air. And then B, you carry out in refractive index 1.33. Okay, now over here the constant speed of light in vacuum is given. Okay, now for the first part. Okay, frequency given. Okay, so we can determine the wavelength by using the wave speed equation. Okay, so for general equation, okay, this will be equivalent to V equivalent to F lambda. So over here V we replace with C lah, which will be speed of the light. Okay, F given, so therefore we can determine the lambda. So which will end up with 520 nanometer. Okay, so once we have the value of wavelength, we can calculate the fringe separation lah. Okay, just simply apply into the equation. So which will end up with 1.08. Okay. Okay, now for B. Okay, so for question B, like previously explained, what will happen is that when we have the experiment submerged in water, okay, basically the wavelength will changes lah. Okay, so you need to determine the new wavelength, so which will end up with shorter wavelength lah. Okay, so this is the wavelength in water lah. So once we have the value of the wavelength, okay, so you can insert back into the equation, okay, so which will end up with the separation of the dark fringes, so which will end up with much more smaller value lah compared to you conduct the experiment in air. Okay,